So this video is a continuation of the last video, and the directions are to find the general antiderivative of each function. But in these 6 examples, we're going to be looking at some more advanced functions. They're not just power functions, and we're going to talk about how to find the antiderivative of these functions. So our first one is the square root of x plus 4x squared, and we're trying to find the general antiderivative. So this has a square root function in it, so before we compute the antiderivative, I would first rewrite the square root of x as x to the 1/2 power. It's going to be easier to compute the antiderivative if we have this written with its exponent form, x to the 1/2. So now we can go ahead and compute the antiderivative. And remember, we're going to start by basically adding 1 to the exponent. So I'm going to put that adding 1 here in red. So we're adding 1 to our exponent. So 1/2 plus 1 will give us a new exponent of 3/2. So we know the antiderivative is going to have an x to the 3/2 power. But remember, if I check this, the derivative of x to the 3/2 would be 3/2 x to the 1/2. The x to the 1/2 is exactly what we want, but we don't want to have a 3/2 here. So we talked about this in the previous video, how to basically undo multiplying by 3/2, we could divide by 3/2. But isn't that essentially the same as just multiplying by the reciprocal? So I think it'd be easier to just write this as 2/3. We'll multiply by 2/3. 2/3 x to the 3/2 power would be the antiderivative of x to the 1/2 power. Look at your second term. We have a coefficient of a 4, so we'll just leave the 4. And then when we add 1 to our exponent, 2 plus 1 tells me this came from an x to the 3rd power. But again, we don't want to end up with a coefficient of a 3, so we'll multiply by 1/3 to undo that multiplication. And then we'll have plus a constant. So our general antiderivative, when we simplify, looks to be 2/3 x to the 3/2 power plus 4/3 x to the 3rd power plus some unknown constant. Remember, you know you need to add the plus c anytime they ask you for a general antiderivative. And then let's just go through the check to be safe. Once again, you can be doing the check in your head. You don't necessarily have to write this down. But to compute whether or not we've done this correctly, we would find the derivative of our antiderivative function. So if we do the derivative of 2/3 x to the 3/2, the 3/2 would come in front and be multiplied by 2/3. 2/3 times 3/2 will just give you 1. And then if we subtract 1 from our power, that leaves us with x to the 1/2 power. Plus the derivative of 4/3 x cubed, the 3 would come in front, be multiplied by the 4/3, so that would leave us with just a 4, x to the 2nd power, and the derivative of a constant is 0. So sure enough, when I computed the derivative, I ended up with the original function that we were given, so that tells me that my antiderivative is correct. Our next example, the function is 3 cosine of x minus the sine of x. So we don't have powers in this case, we have some trig functions. So we really just have to be very good at our derivatives in order to be good at antiderivatives. So this might be a case where you have to bring out some old flashcards that you made previously in the semester when you were really working on memorizing your derivative rules, because if you know your derivative rules really well, then your antiderivatives are going to be pretty simple. So remember, the first term is 3 cosine x, so I'll just leave the 3 as my coefficient, and I have to think to myself, what function had a derivative of cosine? And the answer to that is sine. The derivative of sine of x was cosine of x. So therefore, the antiderivative of cosine x will give us sine of x. Okay, our next term is a minus sine of x, or you think of it as a negative sine of x. So what function had a derivative of negative sine x? And that was positive cosine of x. The derivative of cosine of x was negative sine of x. And then we need our plus c because we're looking for the general antiderivative. So not a lot of work to be shown on a problem like that. It just relies on us remembering our derivatives, so therefore we can work backwards and get our antiderivatives. Same with e here. Our function is 4 divided by 1 plus x squared. So in this case, my coefficient, like I've been showing you, where you just leave the coefficient in front, I would do the same here. My coefficient really is a 4. So this could be rewritten as 4 times the quantity 1 over 1 plus x squared. So when I compute the antiderivative, I'll just leave the 4, which is my coefficient, and then my task is to see if we remember what function had a derivative that was 1 over 1 plus x squared. So you might be needing to pull out your notes with all your old derivative rules on them if you haven't used these in a while. But there was a function that we had memorized, its derivative, and the derivative was 1 over 1 plus x squared. And that function was inverse tangent. So the antiderivative of 1 over 1 plus x squared is inverse tangent of x. And then, of course, general antiderivative will plus c. Again, no work to be shown. It really relies on us remembering our derivative rules. Same thing here for f. This function is 6 times secant x times tangent x plus 4. So my antiderivative, I'll leave the coefficient of 6 in front. What function had a derivative of secant x times tangent of x? Hopefully you remember that was the function secant x. The derivative of secant was secant tangent, or secant x times tangent x. Then moving on to a 4. 4 is a constant. It really is 4x to the 0 power, but we don't have x to the 0 power written because that would equal 1. So if I add 1 to that exponent, that means that this must have come from an x to the first power. So the derivative of 4x to the first power would just be 4, which is exactly what we want. So again, don't forget that plus c, because we're looking for the general antiderivative. So my general antiderivative would be 6 times secant x plus 4x plus c. This next function is 5 to the x power times the natural log of 5 minus 3 divided by the 4th root of x. So like we did in our previous example earlier on when we had a radical, we rewrote the radical in its exponent form. So let's do the same thing here. Before we compute the antiderivative, let's just rewrite the second term of this function. So 5 to the x power times the natural log of 5, that doesn't change. But then we really have the 4th root of x, which is x to the 1/4 power. But because it's in the denominator, when I rewrite that in the numerator, that becomes 3x to the negative 1/4 power. So we want to rewrite the terms with exponents whenever possible. Now we'll move forward with our antiderivative. Now be careful, because this first term, 5 to the x times natural log of 5, that's another one that we have to really rely on our memory of what kinds of functions had derivatives in this form. And so this comes from the derivative of an exponential function. So let me just remind you what you would have learned earlier. The derivative of a to the x power is a to the x times the natural log of a, or the natural log of the base. And this is exactly what we are given in this first term. We have 5 to the x power times the natural log of 5. Therefore, where did that come from? The original function must have been 5 to the x power. So the antiderivative of 5 to the x times natural log of 5 is 5 to the x power. Now let's move on to our second term. So we have this minus 3. I'll leave that as my coefficient. And now we have a power, x to the negative 1/4 power. So I'm going to add 1 to the exponent. But since it's a fraction, I'm going to go ahead and write this as adding 4 over 4. So negative 1/4 plus 4/4 will leave me with an x to the 3/4 power. And once again, if I were to check that, I wouldn't want to end up with a 3/4 in front. So if I were to compute the derivative of x to the 3/4, I would have 3/4 x to the negative 1/4. I don't want that 3/4, so I would multiply by the reciprocal, and the reciprocal would be 4/3. And then don't forget that plus c, since we're looking for the general antiderivative, so plus c. So let's simplify all the way. Our antiderivative, capital F of x, would be 5 to the x power minus 4x to the 3/4 power plus a constant. Once again, you could check this by computing the derivative of our answer and making sure it would be equal to the original. Now look at example H. The function is 3x plus 1 times x minus 4. So there isn't any product rule for antiderivatives. So this is a function where we actually need to do a little bit of algebra first. So I would recommend that we distribute, go ahead and multiply this expression out, then we'll have individual terms that are being added and subtracted, and we can compute the antiderivative of those individual terms. So if we multiply this out, we'll end up with 3x squared. We'll have a negative 12x plus a 1x, so that's going to be a negative 11x minus 4. So now we have 3 individual terms, and we can successfully compute the antiderivative of each of those individual terms. So our antiderivative for 3x squared, we'll just keep the coefficient of the 3. When we add 1 to our exponent, we will end up with an x to the 3rd power, but then we don't want to have that extra 3, so we could multiply by 1/3. Now, since we've done several examples at this point, if you're comfortable looking at the entire term that you were given, the entire term was 3x squared, and then you know that had to have come from an x cubed, so you don't have to actually write the 3 and the 1/3 anymore. If you're starting to do that in your head, that's great. I'm going to continue writing it just to be clear, but if you are, with practice, getting faster and not having to write out each individual step, that's wonderful. Keep going with that. My next term is x to the 1st power. I'll keep that negative 11. Then if I add 1 to the exponent, that means I would have an x squared, but then I would multiply by a 1/2, so I don't end up with the 2 out in front. And then at the end I have a negative 4, and the antiderivative of negative 4 must have been a negative 4x plus a constant. So my antiderivative here, f of x, big F of x, is going to end up being x to the 3rd power minus 11/2 x to the 2nd power minus 4x plus a constant. Now let's move on to something that looks a lot more complicated. Example I is the function 5x cubed minus the cube root of x, all divided by x squared. So you might be having flashbacks of the quotient rule, maybe nightmares. But I have good news for you. There is no such thing as undoing the quotient rule. That would be a complicated mess. So we're not going to undo the quotient rule here. But again, like the previous example where we did some algebra first, we're going to use the same technique here. We need to do some simplification first. And I'm going to start with the radical, just like I've done in the previous examples. Let's rewrite the cube root of x so that it doesn't have a radical. So that would be 5x cubed minus x to the 1/3 power, all divided by x squared. And then since I'm dividing just by one term, a monomial, I'm going to go ahead and do this division. In other words, I call it term by term division. I'm going to take the first term, the 5x cubed, let's go ahead and divide that by x squared. And the second term, which is x to the 1/3, let's go ahead and divide that as well by x squared. So we're doing term by term division, and we're going to simplify this expression. So we realize that we are dividing, therefore we are going to be subtracting our exponents. So just be careful, especially with the second term, since it has fractions. So 5x cubed divided by x squared is just going to give us 5x to the 1st power, minus, here we have x to the 1/3 minus, dividing by x squared, so we're going to subtract our exponents, 1/3 minus 2, So just be careful so you don't make some sort of a silly computation error, especially with the fractions and the negatives. So 1/3 minus 6/3 leaves us with x to the negative 5/3. So this will simplify to be x to the negative 5/3 power. So now that we have successfully simplified the function and we have two individual terms, we can move forward with our antiderivative. So we'll keep the 5. This is an x to the first power. So if I add 1 to my exponent, then that would mean I have an x squared. Therefore, I need to multiply by 1/2. So the antiderivative of x to the first is 1/2 x squared. My second term, I have an exponent of negative 5/3. So again, think about adding 1. So that's essentially adding 3/3 to our exponent. So that would leave me with an x to the negative 2/3 as my power. But then in front, that means I would need to multiply by the reciprocal of negative 2/3, which would be a negative 3/2. And then we'll have plus our constant. So our antiderivative in this case, 5 times 1/2 will be 5/2, x to the second power. Then we have a negative times a negative 3/2, so that would be a positive 3/2, x to the negative 2/3 power, plus our constant. Now the only problem with a function like this, it's not as easy to check, because if I compute the derivative of this function that I have as my antiderivative, I'm not going to get a function that looks like the original, because the original function was in a different form. So when I go to check this, I'm going to end up getting a function in the form where I had simplified. So you really have to make sure that your algebra in the beginning is accurate.